Yeah, let's start meta-analysis. Some of you in my network, PhD students, MSc students might like to have more information about how to do meta-analysis. As usual, I'm going to share with you lecture notes from Professor Carl here at the University of Nebraska-Lincoln. Enjoy the discussion. He's really making very nice updates about meta-analysis. So here we go.
All right, so two events that seem to have defined and stimulated meta-analysis in psychology. Most other areas piled on afterwards. 1952, Hans Eysenck, who was wanted to change the way psychotherapy was done, and thought the way to start was by saying everything we've done up until now sucks, so we should follow my ideas. Every teenager comes up with that idea, and so do many professionals. Reviewed the available literature and concluded there was no favorable effects of psychotherapy. Guess how that went over. 20 additional years of empirical research failed to resolve the debate, just to put it in quotes. That would be today's understatement. 78, Gene statistically aggregated the findings of 375 psychotherapy outcome studies conducted during those 20 years. Glass and Smith concluded that psychotherapy did work. Glass called it meta-analysis. A meta-analysis is an analysis of analyses. Instead of an analysis of data, it's an analysis of analyses. That's the part we have to get used to first, is the nature of a meta-analysis. In a meta-analysis, the case is an effect size. Now, 10 years ago, when I gave this lecture, I would have said a meta-analysis, the case, is a published research study. But that has changed importantly in several ways. A meta-analysis has as its case some effect size. Those are the people or the rats or the cities or whatever, but that's the case, is an effect size. Glass built on a bunch of things. The earliest version of meta-analysis goes back to 1944. R.A. Fisher was a biologist who did an awful lot of what we think of as ANOVA. He took a statistical model and he gave it to biology, and psychology was standing right there with their hand out. When a number of quite independent studies of significance have been made, it sometimes happens that although few or none can be claimed individually as significant, yet the aggregate gives an impression that the probabilities are on the whole lower than would have been obtained by chance. Now this is 1944. This was before p less than 0.05 became magical. Back then, you cranked out an exact p-value by actually doing the semi-partial deviation, differentiation, and you looked at it and you said, yeah, that's small enough, I think I'm going to reject the null. I'm going to treat this as evidence that we have something that we wouldn't expect by chance alone. So that's why it doesn't say anything about p less than 0.05. It wasn't inculcated yet. So the idea was that you could take effect sizes, that you could take p-values. Back then there were no effect sizes. Nobody thought about effect sizes. The only time you got an R is when you calculated a correlation. There was no D. And so this was the idea that maybe we can do something in aggregate. Cochrane, who was the other person who did a lot of what we now think of as ANOVA, figured out a way of aggregating means. So we would aggregate a mean for one group across studies, aggregate a mean for another group across studies, and compare those aggregated means. The magic in both of these bits of math is the sample size that results from aggregating across studies. Because that meta-analysis gets credit for every participant in all of those conditions. So now instead of 20 and 20 or 60 and 60 and 85 and 32, now it's 10,000 and 11,004. As you might imagine, it's easier to reject the null with very large sample sizes. And that was the principal argument. Cochrane laid out much of the statistical foundation of modern meta-analysis, including inverse variance weighting, which is a way of taking sample size into account. Everybody agreed that larger samples are more believable. So larger samples, studies with larger samples, should get more credit or have more of an influence in the meta-analysis. But how are you going to do that? How are you going to weight things? And Cochrane was the one who gave us inverse variance weighting, which has become the principal tool. So we go from, since this is all about p-values, let's get a better p-value by aggregating, to, since we're really trying to compare means, let's get a best possible estimate of those means and then compare those, taking the sample sizes that influence the different means into account. When you read a literature review, what you typically see is the literature divided up into three categories. These are the studies that found the effect that we'd like to think is true. Here's the studies that got a null, and here's some of the weirdos that happen to get it backwards. Notice that that is all based on significance testing. We know that significance testing is not what we do best, especially now that we know something about power analysis, and we realize that if you take the typical effect size in a behavioral study and the typical sample size in a behavioral study, we've got pretty much exactly the p of 0.05 risk of a type 1 error that we thought we had, but we have roughly a 60% chance of a type 2 error. So, if only we had some way to take care of this huge risk of type 2 error, which is nothing other than a power problem. And that's what meta-analysis is going to do. Significance testing is not well suited to this task because it's highly dependent on sample size. Most errors are type 2 errors, and there's a question of comparability of studies that are the same study. Meta-analysis changes the focus to the direction and magnitude of the effect. Instead of asking, is there an effect or not? Because if you jack the n up big enough, there's always an effect. Right? The null doesn't actually make sense as a purveyor of truth. If you really measure the entire sample with a good index, the chances that you're going to get the same mean from those two populations is nil. Right? And so chasing null effects, why bother? But what we are going to put our energy into is aggregating the effect size. Because we do want to know whether there's an effect. The reason for knowing whether or not there's an effect is so that we know that that effect size is likely to be 0 or not. It's not going to be 0 when you jack the n up big enough if you have a big enough collection of studies in your meta-analysis. But the question is size and direction of the effect. Isn't this what we're interested in anyway? The magnitude and the direction represented by the effect size. So the effect size is going to be our chattel in a meta-analysis. Meta-analysis is applied to collections of research that are empirical rather than theoretical. There have been some wonderful attempts within the qualitative research to come up with ways of doing things that are roughly parallel to meta-analyses. It's a little tougher because linguistic aggregation is harder than numeric aggregation, but there's been some good work done. And if you are a qualitative research type, you should check that out. Produces quantitative results rather than qualitative findings. In other words, we're going to have a number that represents what we think is going on in the population. And to quantitative people, that's all we ever wanted. We want a single number summary of what's probably going on. That's effect size. We'd like an estimate of the chance of an error for whatever we decide about that effect. If we think that effect is real and we're going to treat it as real, what's the chance we just made a type 2 error? If we're going to treat that effect size as not real and we're going to treat it as no effect. What's our chance of a type 2 error? So we still want p-values, but we principally want p-values so that we can get to error estimates. Have findings that can be configured in a comparable statistical form. There's three basic kinds of effect sizes that we're going to see: standardized effect sizes, correlations, and odds ratios. Different research areas like different things. We're going to emphasize the correlation because, as I'll show you, we can turn almost anything into a legitimate correlation. That allows us to aggregate the largest number of studies. So whether you were using correlations, chi-squares, or ANOVAs in the study, we can aggregate all of that. Examine constructs and relationships that are comparable given the question at hand. This is going to be really important. I want to say this a couple of different times. The old meta-analyses had the question and the challenge of what studies to include because those studies are comparable. Modern meta-analyses grab everything they possibly can and ask the question, what does and doesn't produce comparable results? And when we look at the research loop again here in a little bit, remember that was the whole idea. Once you run the study, then you run the replications to see if you can get the same result, whatever you want, when you run the same study. Then you start with the programmatic operational research to see what variations change the results. So since you're intentionally varying things, intentionally trying to change the results or see what does change the results, wouldn't it be nice if we had a statistical technique that allowed us to back that up? Where we could say, well, these are the studies that ran it within group, these are the studies that ran it between group. Look, it matters. These are the studies that had these confounds, these are studies that had different confounds. Oh, it doesn't matter. We get about the same effect size no matter what the confounds are. We need something that allows us to do more than just say, there's my one effect size aggregated across all these studies. If that effect size has variability across studies, we need to know what attributes of the study lead to differences in effect size. And that's the same thing we've been saying since the first time we put the research loop up on the board in August. There's different kinds of research amenable to meta-analyses. There's a couple of these that are really common. There's a couple I want to emphasize. Central tendency research. This gets overlooked. Remember how we talked about, a statement like 53% of females in the world, or 50% of people in the world are females? Where the hell's that come from? I don't remember them asking me. Because we don't ever collect population data. So how does a descriptive statistic get elevated to a population parameter? One very reasonable way of doing that is a meta-analysis. And that's what some people did. It turns out that about 62% of people in skin cancer research are females. How the hell did they do that? They pulled up 18,400 and some studies that weren't looking at males and females and anything. Presents what we think is going on in the population, our chattel in a meta-analysis. No, doesn't actually make sense as a purveyor of truth. If you really measure the entire sample, effect size in a behavioral study and the typical sample size in a behavioral study, we've got pretty much exactly the P of 0.05 risk of a type 1 error that we thought we had, but we have roughly a 60% chance of a type 2 error. So, if only we had some way to take care of this huge risk of type 2 error, which is nothing other than a power problem. And that's what meta-analysis is going to do. Significance testing is not well suited to this task because it's highly dependent on sample size. Most errors are type 2 errors, and there's a question of comparability of studies that are the same study. Meta-analysis changes the focus to the direction and magnitude of the effect. Instead of asking, is there an effect or not? Because if you jack the N up big enough, there's always an effect. Right? The null doesn't actually make sense as a purveyor of truth. If you really measure the entire sample with a good index, the chances that you're going to get the same mean from those two populations is nil. Right? And so chasing null effects, why bother? But what we are going to put our energy into is aggregating the effect size. Because we do want to know whether there's an effect. The reason for knowing whether or not there's an effect is so that we know that that effect size is likely to be 0 or not. It's not going to be 0 when you jack the N up big enough if you have a big enough collection of studies in your meta-analysis. But the question is size and direction of the effect. Isn't this what we're interested in anyway? The magnitude and the direction represented by the effect size. So the effect size is going to be our chattel in a meta-analysis. Meta-analysis is applied to collections of research that are empirical rather than theoretical. There have been some wonderful attempts within the qualitative research to come up with ways of doing things that are roughly parallel to meta-analyses. It's a little tougher because linguistic aggregation is harder than numeric aggregation, but there's been some good work done. And if you are a qualitative research type, you should check that out. Produces quantitative results rather than qualitative findings. In other words, we're going to have a number that represents what we think is going on in the population. And to quantitative people, that's all we ever wanted. We want a single number summary of what's probably going on. That's effect size. We'd like an estimate of the chance of an error for whatever we decide about that effect. If we think that effect is real and we're going to treat it as real, what's the chance we just made a type 2 error? If we're going to treat that effect size as not real and we're going to treat it as no effect, what's our chance of a type 2 error? So we still want p-values, but we principally want p-values so that we can get to error estimates. Have findings that can be configured in a comparable statistical form. There's 3 basic kinds of effect sizes that we're going to see. Standardized effect sizes, correlations, and odds ratios. Different research areas like different things. We're going to emphasize the correlation because, as I'll show you, we can turn almost anything into a legitimate correlation. That allows us to aggregate the largest number of studies. So whether you were using correlations, chi-squares, or ANOVAs in the study, we can aggregate all of that. Examine constructs and relationships that are comparable given the question at hand. This is going to be really important. I want to say this a couple of different times. The old meta-analyses had the question and the challenge of what studies to include because those studies are comparable. Modern meta-analyses grab everything they possibly can and ask the question, what does and doesn't produce comparable results? And when we look at the research loop again here in a little bit, remember that was the whole idea. Once you run the study, then you run the replications to see if you can get the same result, whatever you want, when you run the same study. Then you start with the programmatic operational research to see what variations change the results. So since you're intentionally varying things, intentionally trying to change the results or see what does change the results, wouldn't it be nice if we had a statistical technique that allowed us to back that up? Where we could say, well, these are the studies that ran it within group, these are the studies that ran it between group. Look, it matters. These are the studies that had these confounds, these are studies that had different confounds. Oh, it doesn't matter. We get about the same effect size no matter what the confounds are. We need something that allows us to do more than just say, there's my one effect size aggregated across all these studies. If that effect size has variability across studies, we need to know what attributes of the study lead to differences in effect size. And that's the same thing we've been saying since the first time we put the research loop up on the board in August. There's different kinds of research amenable to meta-analyses. There's a couple of these that are really common. There's a couple I want to emphasize. Central tendency research. This gets overlooked. Remember how we talked about, a statement like 53% of females in the world, or 50% of people in the world are females? Where the hell's that come from? I don't remember them asking me. Because we don't ever collect population data. So how does a descriptive statistic get elevated to a population parameter? One very reasonable way of doing that is a meta-analysis. And that's what some people did. It turns out that about 62% of people in skin cancer research are females. How the hell did they do that? They pulled up 18,400 and some studies that weren't looking at males and females and anything else. And no matter what they were studying in dermatological cancer, they grabbed the proportion of females, put that and did a meta-analysis on that percentage. Make sense? There's all kinds of central tendency research meta-analysis that would be better than us saying, it's probably about 30%. The data's there. Do the analyses. Between groups contrasts and within groups contrasts are by far the most common. One of the problems is that meta-analyses were designed when nearly all research was between groups analyses. Within groups analyses have some challenges. Within group studies tend to produce larger effect sizes than between groups analyses, part of which seems to be representative and part of which seems to be statistical bias. We've got to sort that out when we get to it. Studies of statistical association between variables. This is when people are looking at correlations. It's sometimes called individual differences analysis instead of groups comparison analysis. It's the other half of the world. But it also includes measurement research, psychometric, edgeometric, econometric research, where sometimes what you're doing the meta-analysis on is the reliability or the validity index of a study. More and more often, people are asked to do a Cronbach's alpha on the instruments that they're using in their master's and their dissertation, or maybe all of their research. It's become pretty common to collect your data and put it into the database in item form so that you can look at various psychometric statistical summaries. Because of this, we're able to go back into the literature and find everybody who used a particular index and put together a meta-analysis to see in what populations or in what uses or under what conditions is there variability in the reliability or validity of that instrument. Anytime you're going to look at a number and say to yourself, I like that number, or I don't like that number, you could probably, with some effort, do a meta-analysis to decide whether the number you're looking at is representative or not, to get that represented aggregated meta-analysis, and then decide how you feel about things. So, the parts of a meta-analysis. Each study or analysis is a case in a meta-analysis. Simple studies will have a single analysis giving a simple effect size. More complicated studies may yield several effect sizes. We're going to show you different ways to get several effect sizes out of a study. The idea is a case needs to be a thing. A case shouldn't itself be an aggregate. Okay? A case should be one thing, not an aggregate of things across descriptive features. And we'll talk. The effect size is the dependent variable. It has to be comparable at studies. It represents the magnitude and the direction of the effect of interest. Direction. Effects have direction. Long ago, we said we're not allowed to say, I expect a correlation. You have to say, I expect a positive or negative correlation. You're not allowed to say, I expect a mean difference. You got to tell me which group's going to have the larger mean, which group's going to have the smaller mean. The challenge is that many effect size formulas and many effect size calculators give you a positive value no matter what. And you have to pay attention to putting a sign on the effect size that captures direction. So you decide, for example, that any time that the treatment outperforms the control, you're going to give that a positive effect size. And then you have to check any that reverse that, you have to give them a negative. Sometimes the formulas and the calculators do that for you. Much of the time they don't. Obviously, when you're asking if results are comparable, you want to keep track of the direction. You might have to do that with some extra effort. The whole idea of an effect size, when we were first talking about effect sizes, is that it gives us an estimate of the direction and magnitude of the effect that's independent of sample size. That was the whole idea. So that we could have one comparison that included sample size, the summary statistic and the p-value, and another one that didn't, the effect size. This becomes really important because some effect size estimates correct for things, including sample size. When I was you, we didn't learn 4 or 5 effect sizes. We learned, I think it was 18. Because at the time, this was just a few years after it had been just a huge rage to figure out better effect size estimates that were corrected for reliability, validity, variance, floor and ceiling effects, invariance problems, on and on and on. Everybody was trying to come up with the one magical effect size. Eventually, the meta-analysts look at the rest of us like the babysitters that they think they are and said, stop it. Don't. Give us a raw, uncorrected effect size, because we've got 10 years of literature that shows that you do a better job correcting for things in the meta-analysis than in individual effect size calculations. So we're going to focus on raw, bland, boring, uncorrected, and then look at correcting for things and comparing things within the meta-analysis. Other important attributes of the study or analysis producing the effect size are the independent variables. We'll have a whole list of these before we're done. But it is things like, was it a between or a within groups design? Was it an experiment or a non-experiment? What matching variables were used? What other statistical variables were controlled for? All of those things. What was the population? What was the setting? What was the task? All of those define the study and may be why results across studies don't replicate. See, what we're doing here is we're setting ourselves up to find replication. What we're doing here is setting ourselves up to explore a failure to replicate if we find it. You're always of two minds in a meta-analysis. You'd like to say, well, I got a whole bunch of stuff, and when I get that one effect size, I'm going to tell you something that's worth you knowing. And at the same time, we're worried that when that goes to shit, we're going to need to be able to explain why different studies got different results. Yes?
Can you include a meta-analysis in a meta-analysis?
Yes. You end up with a fairly small sample. But I have done meta-analyses where what we did is we went back and we took the meta-analytic results, and those were our cases. We had maybe 16 or 18 of them. And then we were describing features of the meta-analysis, like who conducted it, what the population tended to be, things like that. So you could have a meta-analysis. Typically, you don't, because what you don't want to say, okay, so these two people ran these. I want to get all of this and more and give it updated. Because remember, we're working in real time. And I might run a meta-analysis, and you might have access to 50 or 60 unpublished studies that I didn't find. You're going to run another meta-analysis. You're not going to do a meta-analysis on just those and then aggregate it with mine. You're going to start with my database, ask politely, maybe write me a check, and then augment it. Does that help? Okay. Because when you say can you, the answer is yes. The math's there. It's what are you going to get out of it? Strengths of meta-analysis. Disciplined and quantitative approach to combining and comparing empirical research findings. This is the promise. This was the whole idea. Now, if you're a qualitative type or a mixed type, this may be less impressive. But to the quantitative people at the time, who were sort of stuck with sorting articles into three piles, the ones who gave us what we expected, the ones who gave us nulls, and the ones who came out sideways, this was a huge improvement. Because, you sort of counted, if you had a bunch of big effects that were in the right direction and a couple of effects that were in the wrong direction, that's all you could really say is they were in the wrong direction. They may be little tiny and in the wrong direction, as opposed to huge and in the wrong direction. And so the additional quantitative thing became really, really popular. It was a selling point. I'm going to give you a one-number summary of all of this. And I'm going to tell you if that number is reliably different than 0. And then if we need to, we can play other games with that. That was very heartening at the time. Because we were finding that people were reviewing the same literature and coming up with different conclusions. Why? Because they didn't actually review the same literature. It's a non-hierarchical, it's a non-hierarchical approach. It doesn't favor earlier or later studies as a starting place to which we compare other studies. When you run a literature review, typically the literature review either is historical or anti-historical. You say, well, this is what we've been finding recently, but this is what we found in the past. And, primacy, recency, bias effects. It'd be nice to have a technique that doesn't depend on where we start, but at the same time allows us to include that information. Absolutely, one of the things that should go into your meta-analysis database is the year of publication. Better yet, if you can get it, the year the data were collected. Because sometimes there's as much as a 10 or 15-year period. And you might be looking at publications in the 80s, but you're looking at data from the 60s. It's more important to know the data are from the 60s. It may be important to know that the analysis is from the 80s, because we get into peaks and troughs in choosing our analyses. And sometimes we get into a habit and those analyses are fucked up for a few years. And then we figure it out. So it's nice to know both when the data came from and when the analyses and the paper came from. Protects against over-interpreting differences across studies. We're people. We like what we like. There's a tendency to say, those are better studies. I know they're better studies because they found the result I intended. Those 5 studies convince me of what these 80 studies don't. Seriously? But you see that sort of thing. Allow us to evaluate what attributes of a study are related to smaller and larger effect sizes. This is the big deal. When we don't get replication, why? Allows us to better balance concerns about maximum effect size and maximum representativeness. This is one of the reasons that I get pulled in on meta-analyses more than anything else, is at some point we have to decide, what is the next proposal about? Is the next proposal about a research designed to maximize the effect of something, or to study the most representative effect of something? It often depends on where you are in the system. If you've developed a new anything, it doesn't matter. A drug, a product, a training cycle, anything. You want to get started, you want to show that it works. Then you start worrying about whether it works all the time, when it should. This issue here goes back to the difference between the precursor model of how internal and external validity are related and the trade-off model. Sometimes we are in a precursor situation where we need to show this thing does work, at least sometimes. In order to design that study, we'd like to know everything about a study that increases the effect size. It also gives us the Mythbusters approach. Remember Mythbusters? They would take a myth and they would try to represent that myth. And if the myth held up, they were good. If the myth didn't hold up, they went fucking nuts. They started jacking it up, adding this or that or the other thing, typically explosives or speed, until they got the effect. Then they would look at it and say, yeah, that can't be what we're talking about. You know, my favorite one as a farm boy was peeing on a fence. They didn't get it. So they jacked up the voltage going through the fence until they got an effect. They were doing the wrong thing. Any farm kid will tell you that you don't get somebody to pee on the fence early in the day. Why? What color is your pee early in the day? All right? You're more hydrated. It's more dilute. There's not as much salt in it. Salt is the electrolyte that carries the charge. You wait till later in the day when the poor kid's a little more dehydrated. Then you have pee on the fence. Yeah. Science. And what they did is they got it to the point where they were recording a charge, and then they said, no, that's not what the myth is. That's what you can do here. You look and say, all right, what combinations of things gave us the biggest effect sizes? You look at it and you say, no, that's not the study I want to run. You with me? When we do a regular literature review, we don't pay attention to enough stuff from each article. That's the bottom line. You got the effect. Maybe who did it, what lab it came out of, when. Meta-analysis says that shit won't do. Meta-analysis says you must take apart each study. Any attribute of that study that might influence internal, external, or measurement validity might influence the statistical conclusion validity and the effect size. Meta-analysis forces us to slow down and actually review the article, not just look at its effect size. That is probably the most useful part of a meta-analysis, is you don't do a literature review in an afternoon, because we all know how good that is, having all done it. It allows us to plan smarter, more sensitive, and more useful studies, because now we know what differences in the way you conduct the study produce what differences in the results. Isn't that what we always wanted? This is the way to go get that. Weaknesses of meta-analysis, please notice the star. None of these should impress you. Requires a huge amount of effort. Yep. Oh, it sucks. They did a meta-analysis of 100 years of leadership research across the street a few years ago, and I think they coded data for 13 months. When they were done, they had an analysis that nobody had ever seen anything like it before. It pushed all kinds of crap out of the way. Apples and oranges. Comparability of studies is often in the eye of the beholder. It's a guy named Wilson. Wilson was a pretty good meta-analyst, but a huge proponent of it. Did decades of workshops. Lots and lots of people came over because he made it available. He made it understandable. Most meta-analyses include blemished studies, so do most literature reviews. So do most labs. Various forms of subjectivity. No shit. Do you really think there's any more subjectivity deciding what articles to put in your meta-analysis than there is subjectivity in the design of a study? We make shit up as we go along all of the time. That's why we get folks that have been doing research for a while, because their made-up shit is better than rookies' made-up shit. But what if you didn't have to work with even the most veteran made-up shit? What if you could actually look at an analysis and say, you know what? When you do this, you get a bigger effect size. When you do this, the damn thing flips. What studies to include? What study attributes to code? Coding these attributes? Yes. There's massive subjectivity in quantitative research. I expect you've figured that out by now, as we've gone through all the things we've gone through this semester. Often can't obtain study results or can't summarize an effect size. Yes, you can. And if you can't, give me a shot at it. There are some weird formulas and estimates out there. There's layers of this. There's calculations, there's transformations, and there's estimates. You can almost always get to an effect size one way or another. And the analysis of between study differences is fundamentally correlational. You're not studying causal agents between studies. Hell, most of us in this room will go an entire career without running a causally interpretable study. We live in the land of association, informing how we're going to act as if we have causal knowledge. That's the game we play. We know that. And it's a lot more fun to call somebody else out on their use of causal language than to carefully avoid it ourselves. Yes, it's subjective. Yes, it's associative. But you really have two choices. You can take that subjectivity and that associativity and make it worse by using a shabby, opportunistic system, or you can plug it into something that is quantitative and transparent. And you can decide as we get more through meta-analyses and you see what that database looks like, you can decide which you think is more important, the transparency or the quantitative nature. Leads to a lot of arguments among meta-analyses. Why? They're both awesome. So here's your first big thing. You typically start out by deciding what you want to do a meta-analysis about and then changing it 700 to 800 times. Because you've got to make the decision of what studies to include in the meta-analysis. What studies to include define what you're looking at. And there's this great old detective story called The Fruit at the Bottom of the Bowl, where this burglar goes into a home and steals some stuff, and on the way out the door stops and says, I might have left some fingerprints. So they go back and they clean off where they know they were. And they're not sure whether they were in here. And 3 days later, the police find them up in the attic with a trunk open, and they're polishing the fruit at the bottom of the bowl in the trunk. You know how shit sort of gets away from you? The main meta-analysis question used to be, what's the size of the effect under study? Which led to the question, what studies should we include? And the answer used to be all comparable studies. You should immediately say to yourself, oh, there's some of that subjectivity we were talking about. Are studies using different operationalizations of the DV comparable? Experimental versus non-experimental studies, comparable. Different populations or subpopulations, comparable. Different tasks, stimuli, equipment, is comparable? See the problem? How are you going to find the ones? And when you start looking, you find out that you got a stack of articles this big and you ones that big that did very much things that were the same. We suck at rerunning the same study because there's no advantage in it. There's no future in it. Nobody wants to publish a replication. This is a slide stolen from Lipsey and Wilson because I like it, so I stole it. The notion of pure replications and conceptual replications, you have to be able to argue that the collection of studies chosen for meta-analysis examine the same relationship. This may be at a broad level of abstraction, such as relationship between criminal justice interventions and recidivism, or between school-based prevention programs and problem behavior. Alternatively, it might be at a narrow level of abstraction and represent pure replications. The closer to pure replications your collection of studies, the easier it is to argue comparability. Until somebody else comes along and says, you know, when you were looking at this, you weren't paying attention to this variable that we now know is related to the DV. Remember that old idea that everybody else's confounds are your confounds? And everybody else's IVs that aren't your IVs are your confounds? This is that at a nightmarish level. So which studies to include? The main meta-analytic question is now more commonly, what things influence the size of the effect under study? We're not just going to crank out one effect size and decide whether it's reliably different from zero. We're going to be interested in understanding more. What attributes influence the size of the effect under study? That leads to the answer of what studies to include as every study we can find. We now tend to choose every study that we can find that measured that conceptual DV or that conceptual treatment. Usually it's one or the other. If I'm trying to study, say, leadership training, I want to go find everything that used any kind of leadership training, and kind of DV is going to be a variable for me. If I'm trying to study whether somebody gets a particular form of a particular virus, that's my DV, and I want to go find every study that did that, and how they were treated or where they were now become variables. So typically we either pick, there's a treatment we want to track, and any study that used that treatment is part of our meta-analysis, or there's a particular DV we want to track, and every study that measured that DV is in our meta-analysis. Make sense? That's really the only two categories. You know me, I like to get it down to a list, and if I can get it down to two, I sure will. There's two kinds of people in the world, people who divide the world into two kinds and those who don't. Lots of coding from careful methodological evaluation of each study. That is what you really get out of a meta-analysis. We ran a study once because somebody had a whole bunch of money and really cared. We ran a study where we had two groups of people. There was about 30 people in each group. These are all people who had published at least one meta-analysis. We asked them to do a meta-analysis in an area tangential to their own that didn't involve articles that they had already included in meta-analysis. All right, so they're reading new stuff. One group did the full meta-analysis. The other group stopped after building the database. Never did the meta-analysis. You with me? We then compared those groups on what they had learned about the research literature compared to what they knew before they started. There was no difference between the groups. In terms of knowledge in your head, your understanding of that research literature, generating the database is the really important step. All that pain and anguish, which we have a tendency to push off, the proper polite word is delegate. Don't. Do as much of the work yourself as you can afford to, because it's going through, sorting that, deciding how to code it, changing what the coding is, going back and finding another article, rereading an article after you change the coding system. It's that immersion that is the real gold of a meta-analysis. The meta-analysis you end up with, fine. I can't tell you how many meta-analysis we haven't finished over the years because we got everything we needed to get building the database. Hand the database to somebody else. Here, go get yourself a pub. I got what I need from building the database. Said different meta-analyses were primarily used in the past to combine effect sizes from comparable studies, usually to ask if the effect was non-zero. Meta-analyses are primarily used currently to examine relationships between how a study is conducted and the effect sizes obtained from that study. That's the big shift. It's a good shift. So which studies to include? You must have explicit criteria for what studies you include. Those criteria must conform to the standards of your people. If you're going to do a meta-analysis, the first thing to do is decide where you're going to present it. Go there and look at other meta-analyses done in that community. You're going to find that there's some restriction on the subjectivity you're allowed. You might say, oh, okay, or you might say, screw that, and pick another outlet. But start with, what do your people expect? You might do better than they typically do and still not get your shit published. I'm sorry, not get your bliss and glory published. Because it didn't conform to their standards. And if it doesn't conform to their methodological and technique and analytic standards, they're not going to trust what you got, especially if you're telling them that what they did before is wrong. Published studies won't hack it. Because studies remain retaining null or less likely to be published, including only published studies, biases the effect away from effect sizes of zero. That means you got to start tracking stuff down. Again, this is the unexpected gold. You develop relationships with people in your research community. You swap stories about how data are collected. You decide whose stuff you don't trust because they kind of suck, which typically means they overdelegate. We did a meta-analysis just looking at, we sent people out to find unpublished stuff. Based on that, we had them evaluate a series of labs that were all doing the same kind of work. This was all chemistry stuff. And what we found was that the people who had gone out to find the unpublished studies, who learned something about the labs, who interacted with them, had really solid estimates that corresponded nicely with the effect sizes of the studies in the meta-analysis. Idiots reveal themselves. They reveal themselves better in a phone call or a couple of emails than they do in their published work, which is all cleaned up and edited. Potential sources for identification of documents, computerized bibliographic databases. There are databases that are, more and more people are archiving in some form unpublished articles, or at least unpublished data sets. Authors working in the research domain, conference programs, dissertations, review articles. You spend a lot of time poring over other people's reference sections, looking for one more thing that they reference that you haven't. Your computer, whenever you do a word search, you have to remind it not to look for the phrase unpublished, because you search every document for that. Life's easier now that PDFs are written so they are searchable. There are PDF readers that allow you to automatically search for stuff. As soon as that file hits, it runs through there looking for keywords and highlights them for you. Hand searching relevant articles. I don't want to tell you how many times I just sat down and found stuff that we hadn't found using expensive databases and professional reviewers. Government reports, bibliographies, and clearinghouses. You need to have explicit criteria, and then you need to track down everything that you can find. Especially if you're trying to figure out what leads to larger and smaller effect sizes, you need crapped up studies in there to give you variability. Does that make sense? If you want to study whether a teaching technique works, you don't just grab the A students. If you want to know if a remediation study works, you don't just grab the F students. You need variability to find relationships. your first big is what studies to include. Your second one is what information to include in each study. Coding your database so that you know all the important stuff has 4 purposes. The coding will help you identify groups of studies that are replications. Compare studies to understand what design elements are related to the effect size that they found. Adjust or correct individual effect sizes to give more useful values. Correcting for differences in the way the data were collected, the study was run. And it will give you a better understanding of the research literature that you could possibly imagine. Folks who survive the meta-analytic process often say that the most valuable result was that they actually read articles that they've had sitting in folders for up to decades. Well, I always knew what the result was. Well, that really wasn't the result. And by the way, I finally read the method section. I should never have referenced this damn thing. We get in a hurry. Don't do that here. You will see details, similarities, differences, genius, and mistakes in the literature that you thought you knew. What attributes to code? Everything that may be influencing the results and effect size. Obviously, too big. We're going to have to make some choices. Where do those choices come from? Unit 1. All the discussion we had of the elements of a research study that impact external and internal validity are what we're looking for. You got all the words page, you got the validity net, the researcher. All of these give us an idea of things we want to pay attention to. How were the data sampled? What was the target population? Obviously important. But how did they get the sample? Do you think that they got a sample of the population that they went after? How good is that? When they say they had assignment, what kind of assignment? And when they say random assignment, which are the 4 kinds we know? Random assignment of individuals without constraint, random assignment with administrative constraint, random assignment with researcher constraint, random assignment of groups. Those typically produce different effect sizes. So, one list of stuff to consider including, and then other versions of that we also looked at during Unit 1. These are just other listings of exactly the same stuff, because here's where we are. We used to worry about external validity, internal validity, and measurement validity impacting statistical conclusion validity, but anything that fucks with the p-value is also going to mess up the effect size. So, what used to be an issue of statistical conclusion validity is now an issue of effect size influence. All the same things are just as important as they always were. This is just a formula that reminds us that there are individual differences and procedural differences that influence the results that we get. You need to be looking both at how people were different and at how procedures were different. So here's my list. This is the stuff that I start with. I always carry this, and I look and see what else I might need for a particular study. One of the ones that waxes and wanes over the decades is quality of the study. This was just the shit in the 90s. We need to know the quality of the research. So people would make up a list of things that they looked at to decide the quality of the research. Well, if we have a list of things, then we have to decide how to aggregate them. We have to get an entry for each list, each element of the list, and then ignore them and just put the summary in. No! Put the list into the database. If you think that an estimate of the number of publications coming out of that lab that year is part of quality, put that variable in. You with me? Don't use aggregates. Because it might be that you find that there's a negative relationship between effect size and the number of publications coming out of a cancer lab, or a set of cancer labs. There were. The big labs that had multiple grants and were cranking things out routinely had smaller effect sizes than everybody else. When we were sent after that to track it down, it turned out that they were running the treatments for about 80% of the typical treatment interval. If you correct for that, they were getting the same effects as everybody else. The reason we got started is somebody said, look, some of these little labs are getting bigger effects. They must be cheating. See the implication? The finger pointing? You're getting a bigger effect size than the big folk. You must be cheating. It turns out the big folk were short shucking the treatment. Data analysis is fun. So welcome to Wednesday of Meta-Analysis Week. Today what we're going to focus on is the second really important step, the third really important step, which is being able to look at a piece of results and turn it into an effect size for your database. The first big decision is what studies you're going to put into your meta-analysis. And the best suggestion I have for you is everything that you can find. Start reading meta-analyses and read where people tell you they found their stuff. Because there's sort of an underground of where things are hidden. One of the greatest examples, I think, ever of somebody who was always able to find a data set to test a hypothesis he cared about is in the book called Freakonomics. I don't know how he tracked down some of those databases, but he was amazing at finding a data set. I know somebody who went to a couple of his talks, and he said that he's got an underground of thousands of people, and he basically sends out an email and says, does anybody know where something like this is? And meta-analysts have said that they have similar sort of networks that they feed off of each other. And so if you stay in that sort of research, you're likely to build up membership in a research community like in other communities where you know stuff because your community trains you up. But a really good place to start is where other people have said they have found things. The second big step, of course, is to decide what information you're going to code, keep, and analyze for each study or each meta-analysis. And the idea is there, anything that you think may be causing effect size differences across studies. Now we're going to start talking about some of the theories and the logic behind why effect sizes vary across studies when we look at the actual meta-analysis on Friday. We're going to see that there's two basic notions. One is the notion, which has sort of fallen off the table, that studies ought to replicate each other because they're basically the same study being repeated. And within that notion, the difference between effect sizes of replications is error. There's no good reason that different studies find different effects. Then there's the more realistic, that studies probably aren't really good replications of each other, and there are reasons. Now, we've played the same game ourselves. When we talk about who we're going to sample into a regular piece of research, where we have a population we're trying to represent, we get a whole bunch of people, and we don't expect those people to all have the same score. Because people are different. In fact, the primary game that we play is how do we sort them into groups that are different, or how do we line them up on continua that are different? ANOVA-type stats and correlation-type stats. Because we believe that not only are people different from each other, but they are reasonably, lawfully, predictably different from each other. And then all of behavioral sciences is an argument about what variables you should pay attention to capture differences between people. It's not going to be any simpler in meta-analysis. By the time you go through and make all the decisions that have to be made to create, complete, and analyze a data set, the results of that data set is probably near as complicated as an organism. And so we shouldn't expect that this is going to be simple. Just like none of you collect data across the entire spectrum of social psychology. You're probably not going to be able to collect data across the whole spectrum of how studies differ from each other. Different people focus on different things. I spent years doing meta-analyses with people, the whole idea of which was to try and understand why effect sizes from non-experiments and quasi-experiments were routinely larger than from true experiments. That isn't what we were taught. A true experiment has control. You've got random assignment, you've got manipulation, you've got control, you've got less error, you've got multivariate statistics to control the error further. Why the hell are non-experiments routinely giving you stronger effects than experiments? Do you know? Yeah, you do. Let's look at it. If I have an independent variable, I randomly assign and manipulate who's in what's condition. This is a true independent variable. This is a foot stomper. This is a true independent variable. It's not related to anything. So, how many causal agents are operating in this study? One. Now, let's say that this is a grouping variable. Say it's whether or not you came to a review session. We can randomly assign and manipulate that and run a true experiment. Done it a million times. Or we can say, before you take the test, who came to the review session? Just mark it on the top. When you type your name in, tell me whether or not you went to the review session. Now I've got a grouping variable. Is that an IV? Is that an IV in the independent variable sense of the word? No. It's deeply dependent upon a whole bunch of things that are likely to all be related to exam performance. In a true experiment, I've got one causal agent. In a non-experiment, I've got God only knows how many, and they are pushing typically in the same direction to a different extent depending upon how correlated they are with each other. Because if you start collecting a lot of other variables, you discover that the people who show up for the review session tend to have done more homework, tend to spend more time on this or that, blah, 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 all of which are causal agents that are driving the outcome. You with me? Now, once you say that, it's like, well, no shit. But proving that to the education community was 10 hard years, a lot of which were meta-analyses. I wasn't looking at all the cool things that described the samples. I was just looking at the cool things that described what led up to taking the test. I missed all kinds of stuff that I know is important for predicting a test score. But at the time, I was studying a thing. So once again, what we see is a really important parallel between empirical research and meta-analytic research. You got to start with a population. You've got to have a sampling frame that you can defend. You got to pick the variables that you can defend, that are going to be rich enough to give you a story that's nearly as complicated as the phenomena you're trying to study. This is one of the reasons for looking seriously at meta-analysis, because it reminds us the nightmare we've gotten ourselves into. Because in order to do the study of individual differences or group differences well, we have to study methodology to do that research. It's not enough to know, hey, I know between and within groups designs. Sure, which one are you going to use? One of them. How are you going to choose? One of them. To be researchers, we have to become methodologists. Seriously. Most of you won't have a career that allows you to spend your time rolling around in the methodologies of 30 different research areas. You're going to have to first learn what your kind, what your people expect. But then you got to pay enough attention, largely through collaborations, taking courses in different departments when you're still a graduate student, so that you can push the boundaries of your people and bring in things that might add to it. But don't think you're done with methodology when you're done with the methodology courses. The very best researchers are constantly improving what they know about methodology. Meta-analysis, done properly, is a great way to get a handle on all the different ways that people are doing things. When you start coding those variables, you are going to notice shit that you didn't notice when you read the title, the abstract, and the first and last 3 paragraphs, which is all you need to get that paper into your term paper. Then it comes down to cranking out effect sizes, and that's what we're going to focus on today. The actual meta-analysis itself is pretty easy. Even if you do simple versions on Excel, which is what we're going to focus on Friday, certainly if you're using big, expensive statistical packages, it's no harder than any other statistical package. You got a database, you say put these variables into the model, and it does. It's the buildup that's the big deal. And for reasons that I don't completely understand, people get all whiny about the buildup and the subjectivity of the meta-analysis in ways that they don't get whiny and concerned about the buildup and subjectivity of every empirical study ever done. Recognize that you are living in a land of subjectivity. Not only is it subjective, but it is a victim of fads and fashions. I can't tell you how many things in teaching have been sort of set down and aren't done anymore. Not because anybody showed they don't work, just because we moved on to something cooler. And the next half generation wasn't taught that these 5 things that rocked 10 years ago still rock. So one of the hardest things to do when you're young is to separate the reasons to study things. One of the best things you can do, this is career advice from an old guy, look at the classic phenomena in a new way. Because those classic phenomena aren't solved, and the new way is a new tool. I don't know how many of you have yards. I have a yard, and I like yard tools. I love yard tools. I have yard tools that I don't need to have, just to fuck with them. For years, I did not have a trimmer. You know that little thing that cuts along the sidewalk? It makes really I did it with this and that and something else. I just didn't like it because I didn't want another small engine that I had to maintain, and I hate cords. Well, now we have battery driven. And I went out and bought one of these things that happens to use the same battery as my father-in-law's chainsaw. We were pretty clever about this, because who uses a chainsaw and a trimmer at the same time, right? Now that I have a trimmer, I can't believe I lived without one. And that's the way you're going to feel about learning new methodologies and new statistics. You've got to commit yourself to learning more shit than you know when you graduate. And I'm telling you, meta-analysis will drag you into the future. Every time you do a meta-analysis, you're going to see choices, samplings, techniques, software, theories that you hadn't run across before. Everything's in the literature, but we don't read the literature the way we should. We read the abstract, the title, and the first and last 4 paragraphs. Sometimes we'll go look at the method section to see who the population is. But there's more in there, and especially when you're little, you got to build that up as fast as you can. And so a meta-analysis is one of the best ways I know to know more about the literature than everybody you're in the room with. Remember, that's our goal, to be the one in the room. All right, so let's look at effect sizes. That's my official cheerleader effort for the day. The first time I heard that, Gene Glass had about 6 beers in him, and he made me look uninterested. This is somebody who just spent 5 years dropping something on the planet that he wasn't sure if they were going to tolerate it or not, and he was getting great feedback. So he was a little enthusiastic. All right, effect sizes. we're going to use capital ES to mean whatever sort of effect size we mean at the time. The reason that that is used is because once you calculate the effect size, the way you operate on them, doesn't really care what kind of effect size it is. So you're going to pick a kind of effect size and calculate it. Then when you have them all the rest of it just says ES. So we got 4 kinds of ESs, and then interpreting, transforming, adjusting, right? Because the processes you apply to them really don't care which one it is, for the most part. So let's take a tour. The tour has 2 intents: to expose you to them and give you an idea of how to calculate them. The computator has lots and lots of different ways of getting to an effect size. More than you've probably paid attention to. More than is really fun to sort out. And so, because I love you, I made you this. This is examples of the 10 most common things you start with, what you use in the computator to calculate D's, and what you use in the calculator to calculate R's. Your homework is basically supported by this. I don't expect you to have all this stuff in your head, but I do expect to pick up a handout and go digging through and find the one that matches and go from there. There's one of these that may be a problem, and I'll tell you about that. We have some root rot. Somebody has taken something off of their web page. But I'll bet you I can beg us another version. So, kinds of effect sizes. The D, the standardized mean difference, is the one you're most likely to see given where y'all are from. It's particularly used in education. The D is basically a z-value. What it does is it represents the difference between 2 groups in terms of the standard deviation. So how big is the mean difference in standard deviation terms? We'll look at it more. It was built for between groups designs. Within groups designs are a pain in the tuchus because there's 2 different logics to use to calculate effect sizes from a within groups design. And I'm going to tell you this, and we're going to go over it carefully because part of our problem, your problem, not mine, part of your problem is going to be that very often people have been trained in one of these or the other and don't know that there's 2. And so you're going to have to make a decision, sometimes deciding whether to match something or do what you think is best, but you might have to ask, so what the hell did you do? And they'll look at you like, I ran a standardized gain score. How? What do you mean, how? You have to get it out of them as politely as you can. The one that I tend to use most often, and the one we're going to emphasize in here is correlation. Same way we emphasize that when we were talking about effect sizes in units 2 and 3. The reason is you can put more different things into an R. If you have a 2-group design, you can make a D. 2-group design that you use a t-test or an ANOVA on, you can do a D or an R. If you have a 2-group design that you use a chi-square, the D doesn't make sense. If you have any form of correlation, a D doesn't make sense. And so the R is the more generalizable if you want to include analyses that use different analytic techniques. So if you want to get ANOVAs and between ANOVAs and correlations and chi-squares and a whole bunch of other stuff we'll talk about all in one pile, R is the one that's going to work best for you on that. Odds ratios are for binary dependent variables. Odds ratios work better than chi-squares converted to R's. The farther you move from a 50-50 split, the more an odds ratio is likely to be more representative than an R and a chi-square. Also, odds ratios make sense. If you do this, you're 3 times as likely to be successful as if you did that. That's an effect size I can identify with. I don't have to think about small, medium, and large. I don't have to think about conversion error and bias. I just, 3 times as likely, fuck, sign me up. And don't forget that we can do meta-analyses on univariate statistics, means or proportions. We might want to take every study we can find published in APA for a 2-year period and ask, what is the relative proportion of different ethnic groups represented in that literature? The relative proportion of different orientation groups represented in that literature. So I don't care why they ran the study. I'm looking up everybody's method section in the participants, and that's all I'm pulling out of every study. And at the end of that, we offer APA a review of how well their attempt to improve population sampling has worked over a 3-year period. Make sense? The typical reason for doing univariate prevalence studies is to establish population parameter estimates. Because we want to know, how many of these do we tend to have? How many of those do we tend to have? How many of us? How many of them? You can guess at it, you can make shit up, or you can do a meta-analysis. The definition of a useful effect size is that it's standardized. I give you published results, and you can crank out an effect size, and we all get pretty much the same number. That's what I mean by standardized. There's a standard formula and logic, and if I give you all the same results, you all get the same answer in your effect sizes, just like homework. And we have to be able to estimate a standard error. Whenever we calculate an estimate, we have to have some way of calculating by how much that estimate is likely to be in error. That's a standard error. Because when you put an effect size over a standard error of the effect size, you now have a summary statistic, you can get a p-value, and you can decide whether that aggregated effect size is different from 0 or different from any other value that you want to test. So standardized mean difference, a z-like summary statistic that tells the size of the difference between the means of the two groups. It expresses the mean difference in standard deviation terms. So a D of 1 tells us that the treatment mean is 1 standard deviation bigger than the control mean. This is awesome when different people use different versions of the same variable. For example, we're doing a study on, I think it was double-digit subtraction. Whole meta-analysis on different techniques for teaching double-digit subtraction. And there were different numbers of items on different tests. And some tests were intended to be easier and some tests were intended to be harder. And so number correct was unmanageable. Even percent correct was unmanageable because some of these tests are designed to be differentially difficult. But if we crank everything into z-scores, d values, now I've got that one number, and that tells me how different the groups are in something that is pretty much standardized, and I can calculate an error term. When Cohen was oh yeah, okay, it's resolved. Harper, apparently, there you are, thinking you're having breakfast in Harper and Harper Dining Hall, and then you're thrown out into the streets because there's gas. Fortunately, it's a nice warm day. When Cohen was working with Dee, he said, based on a review, notice, a review of the applied social psych literature, that's what he was focusing on, 0.2, 0.5, 0.8. So a medium-sized effect is half a standard deviation. Like our 135 for correlation, it's not standard across all research areas. You got to know how big of an effect is considered how important in your research area by your people. These are the most common formulas for it. It starts out reasonably enough. What's the difference between the means? And then taking into account the variability. That S is a standard deviation of the difference between two means, the standard error. There's a wide variety of D-like effect sizes not are equivalent. Some are intended as sample descriptions, while others are intended as population estimates. Define and use the different ends carefully. Make sure you know what's going on. Compute the variability of the mean difference differently, and correct for various potential biases. Before the so the effect size people got into it before the meta-analysis people had a strong foothold. So we're calculating effect sizes, and we want a really good calculation. Because remember, this is post-Sputnik. This is during the time where we dare not waste any study. We're in a big hurry, which showed up in academics as publish or perish, which isn't really publish or perish. It was get something out of every expensive data set. That's what drove publish or perish. And so, if we're not going to replicate the way we know we should, we need each effect size calculated from each data set to be as good as possible. And they're off, trying to figure out how to take a D and give you a better version of D that corrects for measurement bias, inter-rater reliability bias, blah, 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 any frickin' thing you can name that might have gone into it. And it's probably not a lie to say hundreds of them, especially if you go outside American and British psychology, because we have junior amateur mathematicians all through social sciences. Somebody'd work up a new one, they'd publish with it, somebody in their research area grabbed it and published with it. When the meta-analysts came along, they said, folks, fucking quit. Quit correcting for different combinations of things with different qualities of corrections. Just publish the information we need to calculate a basic effect size, and we'll clean up all the rest of that stuff in the meta-analysis instead of the effect size estimate. So that's one reason that we're not looking at the whole big panoply of all these different deltas, gammas, gamma D, gamma delta, delta gamma. It's like going down fraternity row. What we're going to focus on is the ones that are going to give you a good estimate of that effect size, and then we'll talk about how to clean things up for corrections and debiasing as we go. The cool thing about working with this is that several people have come up with shortcuts. The pooled standard deviation is the square root of the mean square error. Sometimes they don't give you a mean square error. But if they give you the means and the ends, you can use the means and the ends to calculate a mean square between. F is mean square between divided by mean square within. If you have any 2, you can solve for the third. So if you have the F and you have the mean square between, you can solve for the term you need to calculate it. That formula has saved my ass more than I can tell you. Because until the middle 80s, people did not routinely publish standard deviations for each group. They did not routinely publish standard errors and error terms. You had to go find a way. This worked. This is one of the first pieces of programming I ever did. My Commodore 64 calculated this for me. You can also start directly from a T or from an F. Now, these are the links that are dead right now. I have to figure out a substitute for them. They're really useful because I need a T or an F. Very often, they don't give us a T or an F. The situation where they don't give us a T or an F that's most annoying is in pairwise comparisons in most statistical packages. They give you the mean difference, they give you the standard error of the mean difference, and then they give you a p-value. But if I have the p-value and I have the degrees of freedom, I can plug it into one of these and get the T or the F that I need to work from there. What we're trying to do is create a system within which, if you can bring me a summary statistic or a p-value, I can get you an effect size. And that's why there's so many different versions. There's just so many different places to start based on what someone felt like publishing. D is to beware. If you can get a mean difference in an error term, you can calculate D. Be careful where you get your mean differences. Those ones that we should beware of, you can use them, but make sure you code what they are. Okay, so this is going to be another coding column. Corrected estimates of mean differences from ANCOVAs. If most of your results have been done comparing these two groups using ANOVAs, those F's from the ANOVAs directly give you an effect size. You might come across some studies where, maybe because they were non-experimental, which you should code, they used ANCOVA to correct for one or more potential confounds. If so, the ANCOVA mean difference won't be the same as the ANOVA mean difference. So you can use that mean difference, and you can use a D calculated from it, but make sure that you code that it's an ANCOVA and what variables were controlled for. Does that make sense? Because we're trying to track down and code for every reasonable source of why effect sizes differ from each other. Remember, the effect sizes are our people. That's our population. We're trying to understand why they're not all the same. And obviously, what confounds you controlled for statistically might have an influence on that effect size. Kind of a duh once you say it out loud. Another way that you can get the same thing is multiple regression weights. You can run a multivariate model, we'll do a bunch of this in the spring, where we're representing a group difference, and it ends up giving you a regression weight. And that regression weight is the mean difference after correcting for everything else in the model. So the regression weight from a multivariate model and the mean difference from an ANCOVA are both fine, but they are corrected mean differences. When you have a corrected mean difference, you need to code that it's corrected and what it's corrected for. Same conversation, but starting in a different place. If you can get a T or an F, you can calculate a D. Be very careful where you get your T's and F's. You can use these, but again, carefully code what you represent. So, instead of a regression weight, or in addition to a regression weight, they might give you the T that is the summary statistic for testing if that regression weight is different from 0. Now you got a T, you got a formula with a T in it, you got a D. But that's a corrected D again. Same thing when you get F's that are from ANCOVAs or even factorial ANOVAs. That is that effect corrected for everything else in the model. It's a perfectly legitimate D, but it's not the same as a bivariate D. And anytime you have a multivariate T or F or means or B, you have to code where it came from. That it's corrected and what it's corrected for. Now, part of that same conversation is, where do we get the right effect size for our meta-analysis? Let's say you are conducting a meta-analysis to estimate the effect sizes for comparisons of treatment and control among school children. Most of the time, when people say school children, they mean grade school children. But you check to be sure. Now, here's one study that you found where we have the treatment and control that we're trying to compare. And they've run it in a factorial design where the second independent variable is grade, first, second, third, fourth, and fifth. Our best couple of means to represent treatment for school children and control for school children is down here in the margins. Because this is an aggregate of first, second, third, fourth, and fifth. This is an aggregate of first, second, third, fourth, and fifth. So these are our best means for our study comparing treatment and control for school children. You with me? This is a better estimate than any of these. Now, in a situation like this, I would probably code 6 effect sizes. I would code this one, but I'd also code these and carefully label them, what study they came from and what the different grades are, because you might discover that there's 20 studies out there that all looked at first graders, either just first graders or first graders and other people. Now you can drill down. Do I get the same effect size for first graders that I get overall? You with me? Again, that's that idea of why you are likely to have more entries in the database than you have articles you started from. Instead, you found this article, and in this article, there's our friends, treatment and control, what we're trying to study. And in their factorial design, they had grade school children, middle school children, and high school children. Within this data set, we want these cell means, because those are what we meant by school children. You with me? And those are, I think, the last 2 on that list of 10 different kinds of effect size searches. All right, the standardized gain score. It's like a standardized score, but it's for within groups designs. One of the pieces of language commonly used in within groups designs is gain scores. It comes from the education literature and the developmental literature where time meant improvement. And so it's called a gain score. I take your second score minus your first score, and that's your gain or your improvement. Positive scores mean gain, negative scores mean not gain. The catch is that there are 3 approaches to calculating the standardized gain score. Whichever you use, based on what your people are doing in their meta-analyses, make sure that you code how you calculated that within group gain score. Because one of the things you should be looking at every meta-analysis you get a chance is the difference between the results of between groups designs and within groups designs. Because they don't match. Because there's so much going on. Not just counterbalancing, but all the stuff that goes in your head when you are supposed to be changing populations that you represent. I mean, sometimes we try to do that in a 5-minute reading of something in a laboratory study. Maybe that's working, maybe it's not. All right, so the one is to use the same pooled error term as we used in D. This gives you an effect size that is strongly tied to the statistical significance test. A within groups analysis has a smaller error term, typically, and a larger effect size than a between groups analysis. In other words, if you took the same set of data, put it through a between groups T and a within groups T, the within groups T is going to be bigger, and so will be the D. Because less, there's more. What's called error over here is split into 2 parts, only one of which is error in the within. So, people like that because it follows the statistical power advantage of a within groups design. Okay, but it virtually guarantees that you're going to end up concluding that your within groups designs are stronger than your between groups designs. And they are in terms of error estimate. But they're not necessarily stronger in terms of mean difference. And we're here to calculate a mean difference effect size. But this is a mean difference and statistical advantage effect size. And so some people don't like it. You can go grab the error term and use that as the pooled, which is exactly the same thing as that. Because you're basing your error on the statistical power of the within groups design. The other thing that you can do is you can calculate the pooled using this statistical formula. What that does is that it gives you a variability that is not pushed around by the within group variability. The problem is you have to have the correlation between the two scores that went into the within groups t-test. The statistical packages crank them out. If you run a within groups t-test in any package I know, you get the correlation between the group, the two conditions. But not everybody reports that. The three don't give you all the same answer. You have to stop and pay attention to which of these you're going to use so that you can include within groups designs in your study, in your meta-analysis, because I really think you should. Very often we discover that within groups designs aren't serving us very well, that the notion of symmetrical transfer, which is what we hope for when we do counterbalancing, is difficult, mysterious, hides from it, or doesn't fucking exist. I'm not sure which. And so we have consistently looked at that and almost always found different effect sizes on average. So you have to pick a statistical model that's going to let you do that. Our friend R. I like R because I can do damn near anything I want and turn it into an R. I can take T's or F's, whether they're between or within. I can take chi-squares. I can take a correlation. Or I can take a D and turn it into an R. If somebody else did D's for some things, boom, turn it into an R. Sometimes you will see R referred to as eta. Eta is an R-like statistic, but it's more generalizable than R. R, as you know, looks only at the linear relationship between two variables. And when you have a two-group design, the slope is the mean difference. But eta would allow you to look at things like it will let you look at the strength of relationships that aren't just linear. The problem with eta is, because it's not tied to linearity tests, it has no sign. Anytime you calculate eta, you get a positive value. In fact, in many computators, no matter what you plug in, your R is positive. So you have to keep track of the direction of the effect and make sure that that's represented in the meta-analysis. I have on 3 different occasions brought up the question of, really? All 600 of your meta-analyses yielded a positive R? Nobody got the results backwards? Only to discover that, oh shit, they didn't know that etas and R's always come out as positive in most calculators. And so about 80% of their R's were good, and the other 20% should have been negative. And when you add up a collection of positive and negative things, you get a different average than if you make them all positive before you add them up. Right? And it's sort of moving you away from the null. And so here's a description of that. R is Pearson's correlation. Eta is the direction and strength of the relationship between them, linear and nonlinear. It's always positive. The two converge for a two-group design, but not for a K-group design. So one of the things you want to watch out for is that meta-analyses are typically about the comparison of two conditions. They might be treatment and control, but if you want to compare something to multiple different control conditions, you're going to be running multiple analyses. So when you are coding up your meta-analysis, you got to make sure that you code what was the control group. Just to take us back to the language we used in Unit 3, is it a no treatment control? Is it a standard treatment control? Is it a best practice control? Or is it some specific control focused on some kind of isolation of potential causal elements? Because obviously, the effect size is going to be tied to what you compare the treatment to. Once again, R's and Etas to beware. I always wish this were closer to Halloween. Wear a scary costume for this slide. It's exactly the same slides as last time. All right? With the addition of the K-group design. If you're building an Eta from a K-group design, that Eta only is comparable across studies that have exactly the same set of exactly the same conditions, which is too rare to even plan on. It is possible to calculate a partial Eta, which is the same thing as a regression weight or a partial correlation, as a mean difference in an ANCOVA. It's a corrected effect. You don't want to mix your uncorrected effects and your corrected effects without properly labeling your corrected effects. I've probably said that enough times. All these different kinds of partial and semi-partial correlations, all of which can be used as an Eta, because any R is an Eta. But you got to make sure that any of them that are corrected effect sizes, you are labeling what you're correcting for. I guess I hadn't said it enough times. All right. This is the hardest part of today. Remember how I told you that chi-squares aren't non-parametric statistics? And it was like, well, I was told they were. Sorry. The definition of a parametric statistic is we have some distributional assumption in order to get a summary statistics. That's what we think it is, so we can get a p-value. That's what we think it is. The reason chi-square is a parametric statistic is the only way to get to a chi-square value of a known distribution is to start with a normal distribution and a known number of degrees of freedom. This is like that. Okay? There's something that we've been told fits in one set of labels that really doesn't. Different kinds of correlations. First of all, your friend and mine, the Pearson product moment correlation, and surely you've seen one of these in your hand calculation days. This is the defining formula. It corrects things, or it calculates things into z-scores, and it keeps track literally of the sum of these cross products. So if you tend to be above the mean on both, you get a positive product. If you tend to be below the mean on both, you get a positive product, and it adds up to a big positive number. If you have a negative relationship, then if you're above the mean on one, you're below the mean on the other, you get a negative product, and this adds up to a big negative number. If there is no correlation, then about half the people that are above are below, and about half the people that are below are above, and this adds up to something awful close to zero. Okay? That's our friend. There's two other kinds of correlations. Shortcut formulas. You need to remember that when we were building these different versions of R, they were built not by data analysts and empiricists, they were built by psychometricians. They were built in order to facilitate the analyses of scales and subscales and tests for assessing reliability and validity before high-speed computers. So any shortcut was magical. Thurstone did a dissertation where he did a factor analysis of a 100 by 100 item set. by hand. Inverting that correlation matrix took approximately 80 people, a total of something like 3,000 working hours. Now, it's done before you can get your hand off the enter button. So at the time, any ability to shorten this nightmare was magical. Those are the computational shortcuts. They are applied when one or both of the variables are binary. They are a Pearson product moment correlation. They are a formulaic shortcut to a Pearson product moment correlation. If you take the same data and use any of those models versus the shortcut models, you will get the same result. Okay? They are not another kind of correlation. They are a formulaic computational shortcut. Different from that are formulas that are estimations. In other words, I know I have binary data, but I wish I didn't. I know that if I take two quantitative variables and I reduce them both to binary so that I now have, well, let's have a little more fun. Those are the only four values representing that envelope. I know that the correlation is going to be, correlation estimate is going to be lower than if I leave them quantitative. So we had this set of statistics, very cool fucking statistics, that allow us to say, all right, you ran a binary variable because it was convenient, but you really wish you had a quantitative variable. So what would the correlation have been if you had used a quantitative variable instead of a binary variable? Those are the estimation formulas. You with me? Those are not Pearson's correlations. Those are estimates of Pearson's correlations. These are Pearson's correlations because they are calculations of Pearson's correlation with just a different formula that was faster. The two kinds of analysis, the two kinds of correlations that psychometricians need for their core analyses is I have to know the correlation between items. At the time, this was after introspection had failed, but before psychophysics gave us back the notion that people could use numbers, binary variables were the shit. Everything was binary. Everything was binary. So I've got all these binary items and I need to know the correlations between them. And I need to know the correlation of each item with the total. So the total's quantitative because it's added up, it's a number, and I got all these binaries. So I need two things. How much each of these binaries are correlated to the total and how much they're correlated with each other. Those are the two kinds of computational shortcuts. The point biserial correlation is a shortcut. It's applied when one variable is quantitative and ideally normally distributed, and the other is binary. Keep in mind, it is a Pearson product moment correlation. It's just a computational shortcut. The phi correlation is taking data from two binary variables and getting a correlation-like thing out of it. Phi is not a statistical model. Phi is what we call a Pearson's correlation calculated from binary data. That's one of about 12 things we call phi. We really need more. I don't think we need more Greek letters. We just need people to know more than about 7 of them. It's like there's 7 of them we like, and we're going to keep using those over and over again. If it confuses you, best of luck. What about the rest of them? Nope. So, both of these are computational shortcuts. The point biserial gets us to the total, the correlation between the total and each item. The phi gets us to the correlations among the items with much greater speed. I mean, look at that. That's easy. You can teach somebody to start here and get that in, I think it's 11 button presses plus the variables. Now, the biserial correlation is So, I hear you have a quantitative variable that you like, and a binary variable that you wish had been measured as quantitative. And you'd like to know what the correlation would have been if you'd used a quantitative measure for each. That is the biserial correlation. It is an estimate of what the correlation would have been if both variables had been quantitative. And the tetrachoric correlation. So you have two binary variables, but you wish they were quantitative. You know that the correlation between items on a 7-point scale is on average larger than if those are measured as binary. In fact, you can pretty much march it up the thing. Split it into 2, split it into 3, split it into 4, all the way up to the 10 that you measured it in, and you see that correlation climb. It has a weird curve in the middle around 7, which is why a lot of people who like 7 like 7. It sort of jumps from 5 to 7, then flattens out a little bit. And that's across, God, I don't know how many million simulations. It's fun to have a friend who has a supercomputer that uses SPSS. But this is an estimate. You're saying to yourself, I know I'm underestimating the correlation because I'm using two binary variables. What would it have been if I had two quantitative variables? Some people love this, some people hate this. You have to know what your people think. Analysts, effect size people, all kinds of people, have pointed out that using the R-type or D-type effect size computed from a 2x2 table can lead to an underestimate of the population of effect size. In other words, the more the marginal poor populations move away from 50-50, the more it tends to be an underestimate. And some of us study populations or subpopulations that are not half of the population. Some of us study populations that are parts of a percent. And when you plug those values into chi-squares, you get a decent chi-square value, but you tend to get an underestimate of the population correlation and an overestimate of the error. So when you're underestimating the numerator and overestimating the denominator, you're pushing yourself towards misses, type 2 errors. A very workable alternative is the odds ratio. The odds ratio is usually described as the odds of success for treatment members relative to the odds of success for the control. Now, you see the colorful part down there? The proper language for expressing an odds ratio is as likely, not more likely. If I say that something is 2.5 times as likely, I mean, if this is 10%, this is 25. Okay? If I want to say more likely, I would have said a 15% more likely. This would be 10 plus 15 gets us to the 25. Nobody fucking pays attention to that. We did an auditory analysis where we had a cool system that a buddy of mine built that recorded every commercial on the 3 major networks and 17 cable stations and went looking for more likely and as likely. It just listened for that. In 4 years of data, we found 2 ases. Everybody says more, everybody's lying their ass off. It should be as likely. Now again, like a lot of other things that we treat you the right stuff in here, you sometimes have to be very careful and very polite when you point out that someone is lying, cheating, and stealing. Remember, they either don't think they're lying, cheating, and stealing, at which point we get into a who's right off, or they're lying and cheating and stealing on purpose, and they probably have a well-practiced defense of why we should do it that way. But it's fucking ass. So what we have here is an analysis of data from a local community college where they were interested in whether there was a relationship between gender, and they had males and females together accounted for 99.6% of the population. This was about 15 years ago. We just weren't properly, we probably weren't properly asking information about gender, and I wouldn't be surprised if the population has shifted in 15 years. So we have boring old male and female because that's the data they gave me. It's pretty easy to follow. And then we had traditional or non-traditional, by which we meant age, because they were trying to study to whom they should market the community college. All right. So we got males and females, traditional and non-traditional. We're used to working with proportions. We usually work with proportions for ratio of frequency in the target category to the total. So we would refer to males as 63 out of 288 and females as, under traditional, 40 out of 63 and 102 out of 225. Those are proportions. That's what we compare using t-tests and chi-squares. Odds are computed differently. Odds is the frequency in the target category relative to the frequency in the other category. So for males, we're looking at 40 and 23. If you divide 40 by 23, you see that the odds of being traditional are 1.74 higher than of being non-traditional. And then we can calculate that for females. 101 divided by 123. And here's the thing you have to get used to. In most of the metrics that we use, zero's the middle. Right? You got positive and negative. Here, 1 is the middle. 1 means equal odds. So an odds ratio of 1 corresponds to a proportion of 0.5. If it's over 1, that means it's more likely that you're in the target group. If it's less than 1, that means you're less likely to be in the target group. So now we have odds. And y'all are pretty smart. I'll bet you can guess what an odds ratio is going to be. It's the ratio of the odds. So we have the odds of being traditional for men, the odds of being traditional for women, and that odds ratio is 2.092, which means males are 2.0972 times as likely to be traditional as women. Now, we could have set this up any way we wanted with these two variables. We could talk about the odds ratio of being male or female, traditional or not. You're going to get the same value. This gives us this very nice number. And what this means is that they're going to go target females. Because that was the open market. Worked pretty well, too. We redid this just a few years ago with, I think, 17 different community colleges in New York and California, and I was going to change this because we had multiple categories. We're going to talk about what the different multiple categories are. We had both multiple categories of traditional and non-traditional and multiple categories of both gender and orientation. Nobody would let me have the data. Nobody wanted to have data out there of who was in their schools. Okay. Bastards. Now, one of the cool things about odds ratios is that we have a shortcut formula. We don't have to actually go through and calculate the odds and find the ratio. We can plug it in, and if you look at it, it looks a whole lot like phi. Scaled a little differently. So an odds ratio of 1 means no relationship. Between 0 and 1 means a negative relationship. Between 1 and infinity means a positive relationship. But be careful. I'm sure that someone besides me has told you about being careful whenever you get a percentage. I can lie with percentages. I can really lie with odds ratios, or be horribly mistaken. You need to be careful when considering odds ratios. Beware interpreting large, impressive-looking odds ratios without checking the odds that are being ratioed. Here we find that there's 4 times as likely to succeed in the treatment group as in the control group. I don't want to be in the treatment group or the control group. Almost everybody fails in both. Seriously? We're going to talk about how this is 4 times more likely to be successful than this? No. The lead to this story is, this sucks. It's infinitely better than that, which totally sucks. One of my favorite statistics like this. Let me see if I have it in here. No. Came out, it was on the radio and the news several years ago. Some good data analyst said, people who feed their children more than 4 hot dogs a week, or children who eat more than 4 hot dogs a week, are 8 times more likely to develop tuberculosis. And you're thinking, no more hot dogs, right? I ain't going near 4. We're going to go with 0. Maybe 1 at the park. Can't trust those fucking hot dogs. What were the odds that went with those odds ratios? Well, it was basically 8 in 100 million versus 1 in 100 million. Let's go to a hot dog. So beware of really big odds ratios. Very often they mean really small frequencies. And so if we look at rules of thumb, for D we have the 2, 5, and 8. For R we have 0.1, 0.25, and 0.40. Well, wait, what happened? So the idea is that he started with R, came up with 135 because it felt good. It's a nice even steps. It's easy to remember. We'll be fine. Then fell in love with D, made up the D rules, and I don't know, it was a while before somebody said, don't match. At which point, because we liked D's better than R's at the time, we changed the R. Which doesn't mean any more in this form than it did in the other one. You still have to know what your research community considers big, small, and medium. Odds ratios, those have been fairly stable over the years. More important than these rules of thumb is knowing the usual effect sizes in your research area, what your community thinks is important. All right. Not sure about this. Transformations. This is the same conversation we had in non-parametric statistics, so we're going to do the quick version. All of this adding, subtracting, multiplying, and dividing we're doing works best if the data are normally distributed. When we take an average of a set of things, that average, as representing typicality or middle, is better if the data are normally distributed. Well, the problem is none of D's, R's, or odds ratios are normally distributed. And so typically we transform their raw effect sizes before we operate on them. And so if we're working with D's, we're going to plug in the D, and we're going to transform each D into an effect size using this transformation formula. And it actually shows you the Excel formula. If you're working with R, this is the Fisher Z transformation. This is the same transformation that we used when doing a Fisher Z test for correlations across populations. Those correlations aren't normally distributed either, so you do a Fisher Z transformation before you do the Z test. And this tells you how to do the transformation. The thing is that once you transform the data and you operate on the effect size to get your aggregated effect size, you then have to turn that back into an R. So there's an in and an out. And the same thing for the odds ratios. Odds ratios tend to be distributed like chi-square, not like a normal distribution. And so what we do is we transform it, operate on the transformed effect size. When we get our summary statistic, what we did the whole meta-analysis for, what's that aggregated effect size estimate? Translate it back to an odds ratio. And we'll show you how all this operates on Friday when we show examples. There's all kinds of things that we might be concerned about the quality of our effect size estimates. We might have measurement unreliability. If we're trying to study the relationship between constructs, we know that our variables aren't constructs. Our variables are not perfect measures of constructs. And so we could, if we wanted to, adjust the estimate of the correlation between the constructs for the limited reliability, typically of the DV. We might know that we have a sample that is range restricted. We're trying to study everybody, but we couldn't find everybody. And we think that the people that were available to us are at one end or the other, or maybe just a slice in the middle. That range restriction is going to reduce the correlation estimate. This is a way of correcting for that range restriction. Artificial dichotomization of measures. This is why we talked about tetrachoric and phi. Tetrachoric and phi have a role if we're working with dichotomized measures, we know we're underestimating. We might prefer, especially if we have a mix of binary variables and quantitative variables that are in our effect sizes in our meta-analysis, we might decide that we can put them on a more comparable footing if we translate or adjust our dichotomized measures using biserial and tetrachoric. Again, whether that's a really great idea or a really awful idea depends upon your research area and who taught you meta-analysis. And finally, outliers. Shit happens across studies at least as much as it happens within studies. I've told you a bunch of different stories about simply collecting data from the wrong people. If you collect the data from the wrong people, you probably have an effect size that's wrong too. And so one of the things that people have done over the years is they have engaged in outlier analysis of the effect sizes before they run their analyses. The outlier analyses that work best are the same ones that we used. Our buddies Mosteller and Tukey. Those are still really consistent, really good. Lots of people don't like them because it's a computational step. SPSS and R both have a variation of those that you can just click a button and get. And then most people tend to do Windsorizing because they don't want to lose the data point. Especially after you put 3 hours into coding that son of a bitch up, you don't want to throw it away. I know it's small, it's just a little too small. We're going to keep it in as small because I ain't throwing away those 3 hours. For all of the adjustments, be sure to tell your readers what you did and the values you used for the adjustments. So we put the data in, we may adjust them, then we're going to transform them, and then, finally, we're ready for Friday, the actual process of doing the meta-analysis. We're going to focus on the blandest of meta-analyses. Having a set of studies converted into effect sizes and wanting to know what's my best guess of the population effect size, and is that effect size significant? There's lots of other cool stuff. We'll talk about doing the cool stuff, but we're not going to actually do it. However, I have made for you handouts on several of these things. How to use these different macros that Wilson has developed over the years, and how, because they pull into SPSS and they're done in SPSS, so I made you handouts that kind of look like the other SPSS handouts.
Thank you so much. This has been the first part of the meta-analysis. This is part 1. So we'll have part 2 coming up. I hope, even if there are some gaps in between the recording, Professor Carl made a very good video, a very good audio that's accessible to all. Thanks so much. Thank you, Professor Carl. We wish you long, happy life. And those of you out there, friends in Ethiopia, in other parts of the world, working on statistics or research methods, especially meta-analysis, yeah, you might get something out of this. Good luck. Thank you. This is Fakad Urata from Youth and Education Support Service Ethiopia, University of Nebraska, Lincoln Campus.